Okay, this is the section on exponential growth and decay. Let y of t be a quantity at time t. The rate of growth of a population is proportional to its size. That is, dy dt, that's the rate of growth. Y, remember, is a quantity, so it's it's a quantity over time, is equal to ky, which means that it's proportional. So the bigger that y is, the bigger that your population is that when you're starting, the bigger the growth rate is, because the larger the population, then the larger the next generation of that population. The unique solution to this differential equation is y of t equals y naught e to the kt. K is the constant relative growth, and y naught equals y of 0 is the initial amount. So anytime you see, you probably know this, but anytime you see a subscript 0, that means initial amount, and that usually means that you're plugging 0 into the function, because most functions that we create to model things start at 0. Okay, so we could show, and I have that here, we can show that it's a solution, because when we take the derivative of this function here, we get y naught, the variable, the independent variables t, so we get y naught times k, because of chain rule, times e to the kt, and e to the kt is y. That's here. I'm sorry. This actually is a little bit not quite right, the way I wrote this out, so let me go ahead and erase it. Okay. So we're getting y naught times e to the kt times k, and this right here is y, and this right here is k. So you can see that the derivative is in fact y times k. Okay, so in general, we're going to use this model for exponential growth, and pretty much all population growth is exponential. A common inhabitant of human intestines is the bacterium E. coli. A cell of this bacterium in a nutrient broth nutrient broth medium divides into 2 cells every 20 minutes. A cell divides into 2 cells every 20 minutes. Excuse me. The initial population of a culture is 50 cells. So what that tells us is that y of 0 is 50. That's the initial amount, which is also y naught. And then 2 cells every 20 minutes. Now, I need to foreshadow here. I'm going to be asked to do this in hours, so I'm going to go ahead. 20 minutes is a third of an hour, so y of 1/3 will have doubled. Each cell becomes 2 cells, so this will be 100. And for part A, we want to find the relative growth rate, and the relative growth rate is k. So I'm going to use this information that we got to get the relative growth rate. Y of 0 equals 50 means when t is 0, y is 50, and then we already know that y naught. I'm sorry, that means that y naught is 50. Okay, and then y of 1/3 equals 100 means that when t is 1/3, that's 1/3 of an hour, we get 100 bacteria. And so when we use our model here, our y equals y naught e to the kt, and we put in this information, we get 100 using these ones. So I'm going to use 1/3, 100, and y naught. Okay. So 100, that's my y, equals 50, that's y naught, e to the k times t, so 1/3 t, 1/3 k. And now we just have the one variable k, so we can solve for it. Let's divide both sides by 50, and then we're going to have e to the 1/3 k is equal to 2. And if we take the natural log of both sides, then we have 1/3 k equals natural log 2. And that means that k is 3 natural log 2. We can approximate that, but writing out the decimal is probably more cumbersome than just going ahead and leaving that exact. Part B asks us to find an expression for the number of cells after t hours. So all we're doing there is putting our k back into our model, which is up here. This is our model. So we're going to have y of t equals y naught, which we know is 50, e to the kt, and k is 3 ln 2 times t, and t is in hours. Part C, find the number of cells after 6 hours. That's just y of 6. And y of 6 ends up being 13,107,200. Part D, when will the population reach 1 million cells? So that's asking when is y of t equal to 1 million? And we're being asked when, so that means we'll solve for t. So if we put this, if we look at our model here, we're going to set this 50 e to the 3 ln 2t equal to 1 million. And so we get e to the 3 ln 2t is equal to 20,000. Okay. And then I'm going to do this a little bit fancy, but I'm going to write this as e to the 3. Let me take that back. E to the ln 2t, e to the ln 2 to the 3t. That's what I'm going to do. So the reason I'm doing that is because this e and this ln, they undo each other. So what we have here, when you look at the exponential function this way, when you change the base to not be e, you can see what's happening. It's doubling, okay? Or in this case also, you could also look at, this could actually be 8 to the t. Either way, we're going to take log of both sides, so we're going to get something. We're going to get t equals, whoops. I'm taking the log of both sides, so what I really get is t ln 8 equals ln of 20,000. And so t equals natural log of 20,000 divided by natural log of 8. So if I put that into the calculator, whoops, I'm going to do natural log 20,000 divided by, whoops, end parentheses, then divided by natural log of 8. And I got 4.76, and that's t, which is in hours. Okay. Second example. Experiments show that if a chemical reaction, and the chemical reaction there is given, takes place at 45 degrees Celsius, the rate of reaction of dinitrogen pentoxide is proportional to its concentration as follows. So what they just told you was what is written here. This is our dinitrogen pentoxide. And we're taking the derivative. That's the rate of change of, we've got the rate of reaction, okay, to its concentration. So is proportional to its concentration, and this is the rate, and that's why it's the derivative, okay. So everything in this sentence, in other words, is actually in this equation. Find the concentration of N2O5 after T seconds if the initial concentration is C. So for A, this is exponential growth, by the way. If you remember from the very beginning, this statement here, this statement here, the rate of growth of a population proportional to its size. So that's the same thing going on in this chemical reaction. This is the amount of N2O5, and this is the differential. We just have a negative sign because it's apparently decaying. Okay, so find the concentration after T seconds. So we're really going to have this same model. And we've got initial concentration is C. So there's really, oh, just kidding. This is K. This is opposite dy dt. And this is Y. So what we've got is Y of T equals 0.0005. I did the wrong thing, so sorry. Let's see, what is Y naught? Oh, C. C e to the negative 0.0005 t. So this negative right here, I went ahead and put it onto K. Okay. Really quickly here, this is what y equals e to the x looks like. And this is what y equals e to the negative x looks like. So when K is negative, we get decay. And when K is positive, we get growth. So for part A, find the concentration after T seconds of the initial concentration C. That's just asking us for our equation, so we've got it. And then B, how long will the reaction take to reduce? So how long, that means we're looking for T. Will the reaction take to reduce the concentration of N2O5 to 90% of its original value? So we want to know when is Y equal to 90% or 0.9 of its original value, why not? That's what it's asking. So we're going to have C e to the negative 0.0005 t equal to 0.9, and we're going to solve for t. And there's t, so we can solve for it. So whoops, I forgot the C. why not is C, and there's C. As it turns out, the C's on both sides cancel. That's what happens if you're gonna if you're asking for a proportion, 90% of something or a third of something, then it doesn't really matter how much you started out with. It only matters that, the proportion that you have with at the end. So I'm going to cancel the C's, divide both sides by C, and then I'm going to also take the natural log of both sides here, so that we get negative 0.0005t equals natural log of 0.9. And so then we get t equals natural log of 0.9 over negative 0.0005. And you might worry that this answer is negative, but natural log of 0.9, I'll go up here and draw what natural log looks like. Natural log looks like this. This is the 0.10. And so for these values down here, in between these x values, in between 0 and 1, natural log is actually negative, so that's not actually a problem. Oops. We're going to get t is approximately, go natural log 0.9 divided by 0.0005, and that gives me a negative, but I'm the negative in the denominator, so 210.7. And if we go back to see what the units are, this is a time, and it looks like we don't know. It wasn't part of, oh, we do know, seconds. Okay, I'm going to go ahead and pause this video here, and then I will post the last two examples on a separate video so that they're not too